get it down here. I don't think that they get a spin class rocket one, but I haven't paid that close attention. Okay, briefly here, this here is the dummy mirror for the 4-meter telescope. This is what they put in the telescope when they're trying to balance it all out and everything. Rather than put the actual mirror in, they put this big hunk of concrete in there. Then the Tohono have an artist by the name of Michael Chiago. He painted this thing up here. And basically what it shows is Baba Kivari there, right there, which is exactly due south of us here. That's the Tohono's most sacred mountain. And here the Tohono out in the desert picking the fruits off of a saguaro cactus. This stick that they use here is called a whippeth, and it's actually the sticks that make up a dead saguaro. That's all. It's what's in the saguaro is canes like this. This Tohono are the only one who are allowed to go out and actually take the fruit off of those cactus.
Even now?
Well, they're done fruiting now. But yeah, I mean, like in June or something is when they fruit.
Which one is the 4-meter one? Where are we getting it? That
yeah, it's something right up there. Okay, let's walk a little further here, and then whoever needs to have that. Oh, okay, yeah, I have one more stop before we go up the hill. So if you want to just walk with us, and then you can come back and get your car and drive up there. Are you guys ready? Yeah, that's where you'll end up driving up to the top up there. Okay? Observatory is kind of down at the end of the road here, the silver one and then the white one. Both of those telescopes are part of what they call Project Space Watch. The one on the left is a 1.8 meter and the one on the right is a 0.9 meter, so that's how big their mirrors are. Project Space Watch involves looking into space for near-Earth asteroids, near-Earth objects and everything, trying to locate them before they hit us. Because if we do locate one, there isn't much we can do to get out of their way, but anyway, so that's what it's used for. Actually, over there in the Catalina Mountains there, up on Mount Lemmon, the University of Arizona has what they call the Catalina Sky Survey, and that finds probably about 70% of the near-Earth asteroids that come by us. But it's telescopes like this that frequently go and study them a little further to get a better idea of exactly what their orbital elements are going to be and whether they're going to be a real threat to us or not. So anyway, and the one on the right is the Stewart telescope that was originally down on the campus. It's also referred to as the All-American telescope because it's actually the first telescope that was completely made in the United States. Up previous to World War I, all the telescope mirrors and lenses and stuff were made in Europe, like Germany and France and that. But then after World War I came along, and they decided over here that, gee, it'd probably be a good idea if we could make our own mirrors and lenses and everything. So in like 1921, 22, the U of A hired a company called Spencer Optics out of Buffalo, New York, to make a 1-meter telescope mirror for them, which they did. And so it ended up being down on the U of A campus there. And then in 1963, this ended up being brought up here. And the new telescope just to the right of it. So that's the newer one. Now, why do we care about these near-Earth objects and all that rigmarole? Well, about 65 million years ago, the dinosaurs, they didn't have a program or anything to keep an eye on asteroids and comets and such. And one got by them and hit them, and well, you know the rest of the story on that. It's probably a good thing that we actually got hit, because if we didn't get hit, we wouldn't be here. I'd probably be talking to a bunch of dinosaurs or something. I don't know. Yeah, and I'd be a dinosaur too. So that happened 65 million years ago. Then we go back 50,000 years up to northern Arizona, where there's a meteor crater, or Barringer crater, whatever you want to call it. That was a large asteroid that hit up there and created a hole in the ground about a mile in diameter and 500 feet deep. So that happened. You go back to 1913 in Siberia, in Tunguska. Some object struck up there, and was probably about 20 years before they got into that location because it was so remote and everything. But they went there and looked, and they saw that all the forest up there was just completely flattened for about 800 square miles, and they don't really know what caused that. Then, of course, we only have to go back a few years to Chelyabinsk, where some big asteroid or something came in, and fortunately came in at a shallow enough angle that it spread a lot of the energy over a large area rather than impacting into that town of Chelyabinsk, which probably would have really decimated it. So after that happened, I guess we really found out that we need to find some of these more modest-sized meteors. Up until then, we've been looking for all the big ones, and we found the really big ones, but it's probably these more medium and small-sized ones that could, wipe out a big city anymore that we got to be interested in yet still. So that one that came into Chelyabinsk, unfortunately, it came in from the sun, so there was no way we could see it coming. The day after, we were expecting a meteor to come by, or an asteroid to come by very close to Earth, within about 15,000 miles of Earth. So we were all waiting for that one. But then the day before, this thing comes screaming in and surprised the heck out of us. So you just never know when. So keep your eyes open.
Looks flat over there. Huh? What's that? Uh-huh. Extreme fire danger today.
USA campus up until 63. Okay, this is the Stewart Observatory with the Bart Bok telescope. Bart Bok was a astronomer who was very interested in the Milky Way, which is our home galaxy. So it was in the 1940s that he was asked to write a book on the Milky Way. His wife Priscilla was also an astronomer. So they were working at Harvard at the time, so they asked him to write a book on the Milky Way. So he says, okay, we'll do that. So the idea was that he was going to write like 4 chapters, and then she was going to write 4 chapters, and they'll combine it in a book. So anyway, she got done writing her 4 chapters probably sooner than he got his done, and he came home one night and settled himself on his easy chair in front of the fireplace, and she walked over to Bart with her document and said, here's Bart, I got my work done. And well, he starts paging through it, and before too long he starts getting very critical. And after a while she didn't appreciate that, so she walks over there to him and grabs the papers and everything and grabs them away and walks over to the fireplace and says, hey, if you don't like what I did, I'll just throw them in the fireplace. He says, no, that's okay. So anyway, finally the book got published and everything, and after the reviewers did the reviewing on it and everything, it turned out that the reviewers actually preferred the portions to what he'd done. So anyway, like I say, Bart was very interested in the Milky Way. Now here is a representation of our Milky Way. Now that little red dot is our sun, okay? See where we are in the Milky Way? Yes, it's very small. See where our sun is in our Milky Way galaxy. Okay, see the little red dot there? So anyway, the Milky Way is about 120,000 light years this way, about 1,000 light years thick. We also have a central bulge there too that you can't see, but it's there. So 120,000 light years, what the heck's well, a light year is the distance light travels in 1 year. So after you do all the calculations and everything, it turns out to be about 6 trillion miles. Okay? So when somebody says something is a light year away, or somebody says something is 6 trillion miles away, what they're saying is it's a light year away. And so something that's a light year away actually takes light 1 year to travel from that point to us. Now our sun is pretty close by. It's only 19 million miles away. So at the speed of light, it only takes 8 1/3 minutes to get here. Okay. Our moon, right up there, it shines by reflected light. It's only about 240,000 miles away. So it's only like a late second or so away. The nearest star to us is Proxima Centauri. That is 4.3 light years away. So 4.3 times 6 trillion miles, 24 trillion miles away. That's the closest one. The closest galaxy to us that's kind of similar to ours is what they call the Andromeda Galaxy, which is in the constellation Andromeda, which if you go out tonight, exactly where to look, you can actually see it. If you're in a good dark area, you'd actually be able to see it with your naked eyes. So that particular object is 2.5 million light years away. So 2.5 million times 6 trillion miles away. But that is the most distant thing that a person can see with the human eye. So that gives you some kind of idea of the immense distances of our universe. Nothing's close by. Okay, anyway, one interesting thing about our Milky Way galaxy, and actually all galaxies, is at the center of a galaxy is what they call a supermassive black hole. And it's about 4.3 million times the mass of our sun. So that thing at the center of our galaxy is 4.3 million times as big as our sun. Now, how do they know that there's this supermassive black hole there? Well, using radio telescopes, like I'll show you in a little bit, looking at the center of our galaxy using infrared, near-infrared cameras and telescopes like I was telling you about before, they're actually able to cut through all the dust and gunk that's at the center of our galaxy to see what's going on in there. And what they found was a little spot where there wasn't anything. That's the black hole. But what makes it interesting is the fact that around that little spot of nothing are several dozen, 3 dozen stars that are orbiting that little spot in their very close, tight orbits. And being able to figure out what the mass of those stars are and everything, and determining their orbits and everything, they're able to figure out the fact that there's something really massive that those things are orbiting. And since we can't see it and anything, and we can't really detect it, the only thing that could be that small and be that massive is a black hole. So, and now they've discovered these supermassive black holes in just about every galaxy, and so they're very common. You know, they shouldn't be confused with just your regular black hole.
What's that?
There's more over there.
Yeah. That was the radio telescope. Or radio, what do you call them? The ones there. You want me to pull you up? Or do you want to go slower?
Go slow. Go slow myself.
Halfway up the hill here and stop.
They got a seat waiting for you down there. So they got a seat waiting for you up there.
You would think they would have like a jeep for people to get on.
Well,
Drive them up there.
he said you can drive up if you get a pass.
Yeah, but then you'd miss what he's saying. Another road down there.
Uh-huh. Is that the one we drove up, probably? I imagine. I don't know.
Somewhere in the sky.
Para abajo. Yeah.
All right, we're looking out at a couple of different things here. One thing we're looking out is the Tohono Reservation, which happens to be about the second largest in the country, second after the Navajo Reservation up in northern Arizona and that. Their reservation actually extends down into Mexico as well. It's how many acres here? About 2.8 million square acres of reservation out there. It's also considered to be what they're referred to as a basin and range area. So the basins is the desert area, and the ranges are the mountains you see out there. So what happened about 10 million years ago is the Earth's crust was rather thin down here, and there's a lot of magma underneath it. And what happened was the Earth's crust would stretch and there cracks would develop, like there'd be a crack here and a crack here. What would happen then is the area between the cracks would go down, and the areas on either side of it would rise up. So what went down is the basins, and what went up are the ranges that you see out here. and all of these generally run north to south. Now those ranges over the last 6 million years have been weathered down due to rain and the constant sand beating up against them and everything and weathering them down. So there's like about 5,000 feet of material out there in the basins now of worn down mountain range into them. So that's what that is. Okay, if you look over here to the left, you're going to see a couple of telescopes there in the foreground here. One to the right is obviously a radio telescope with a big dish there. That's part of the BLBA, or Very Long Base Array. And then there's another radio telescope just to the left of it. That's like a 12-meter radio telescope, and that belongs to the University of Arizona. Now the BLBA is interesting because that is like one of 10 identical radio telescopes stretching all the way from the Hawaiian Islands to the Virgin Islands. So when they're spread out that far apart, that's what you call a very long base array. And when you spread them out that far, if they all start looking at the same object, it's like you have a telescope that big in diameter. So you get really good resolution out of it that way. So what do they look at? Well, for one thing, it looks at the center of our Milky Way galaxy, and that's one of the things that they use to determine the fact that there's, like a supermassive black hole in there. It also looks at stars, newly forming stars. Lots of times when they form in these areas where there's a lot of dirt and debris and gas and everything, and you can't see it through the normal part of the spectrum that we can see through, So that's where radio telescopes come in handy, looking through that kind of stuff too. So anyway, like I say, those are radio telescopes, and they operate in what they call the radio spectrum. We have what you call the electromagnetic spectrum. Okay, that's everything from low frequency stuff to really high frequency stuff. Really high frequency stuff is more in the gamma rays and stuff like that, and the low frequency stuff is your radio waves. Our ability to see, we can see somewhere between 400 and 700 nanometers in that portion of the electromagnetic spectrum. So our eyes can only see a tiny little bit of the entire electromagnetic spectrum. There's a lot more there that if you have the right kind of tools to use on it, you can see, such as radio telescopes. Okay, turn around here and we'll be looking up at the bottom of the observatory. So it was construction was beginning in 1967, and it was finally completed in 1973. Now when they prepared this site, they noticed a big crack in the mountain, okay? So what they ended up having to do is drill some holes through the entire mountain, and they ran some big bolts through it. And you can see obviously one of the heads of the bolt right there, about 4 feet off the ground there. Then there's like maybe 1, 2, maybe 3 or 4 more other ones over. So they ran those through and tightened them up, and voila, the mountain stayed together. The other thing they did here was spray this material on here. It's what they call, it's a sprayed on concrete called gunite, at least that's one term for it. So they spray that material on there so that the granite that's behind it doesn't get all worn, and break apart and everything. And I mean, granite makes nice countertops, but it doesn't make mountains that last forever. So they had to do that. Okay.
What's that thing?
It's a GoPro video camera. It does takes pictures too, but video too.
Okay.
And it can take a picture every 5 seconds too if I want to with the video.
Mm-hmm.
But right now it's just video.
So what would you use that for, like, other than your regular camera?
It's good for like does a lot of sport photography. They do a lot of like underwater stuff. They have cases for these. Do a lot of like stuff with cars and stuff too. I do like video mapping. I put them around the car and then can map an area or carry them around their light. Yeah. They can do cinema quality too. Here they have some like do 4K like they do for movies.
How do you like make your frame? It's not totally in your control, right?
It's fixed. No, I can set it like a wide, narrow, or medium, and you can look at it on like a iPod or something too. You'd be maybe up to 600 meters away. You can control them with the radio, Wi-Fi, and stuff. They don't have a lot of air up here? Do you want to push?
No. It's gonna hurt tomorrow.
Okay, for those who didn't get to the solar telescope, that's the atmosphere solar telescope over there in the distance, that angular structure. Just in front of it and to the right, you can see the big catch basin that we use for catching rainwater and snowmelt up here. So what happens is if there's any rainwater or snowmelt in that catch basin, it gets pumped out into that one little building to the left of it where it gets filtered and then sent up to the 500,000 gallon tanks just past that little building there.
Wait, where?
Yeah, that way.
Oh, those like gray things?
Yeah, they're whitish tanks. The road you came up on, in elevation, it probably starts about the 3-mile mark. When you get up to the top here, that's 12 miles, so it's about 9 miles of elevation you came up on. This here is the original construction road, right here, that they brought up the solar telescope on and the 2.1 meter on. And that road from top to bottom is about 5 miles, so you can tell it's quite a bit steeper. It's not used anymore except from up here down to where that Quonset hut is down there. Otherwise, it's pretty much abandoned.
What?
Abandoned.
But what?
But why? Because it's too steep and narrow and windy, and you got this other nicer road to come up on. But you probably won't get killed on, more likely.
Wait, but was the cover so right on it to longitude? Or you close up?
Okay, here we are at the bottom of the Mayall telescope. It was constructed between 1967 and 1973. let's see here. The dome on top, well, the telescope, the observatory is 187 feet high. The dome that sits on top of it runs around 500 tons. The shutter on the dome, 15 tons. The telescope that sits on the pier and there runs around 760,000 pounds. Now the way this is built, this observatory is actually two sections. There's an outer section, outer part of the building, then there's the inner part of the building. Now the inner part of the building is what the telescope sits on, and that's a great big pier that's about 37 feet diameter. It's got like 24-inch walls. And the way they poured that, it's about 100 feet high. And the way they poured that is they used what they call a slip form. So that form was like 37 feet diameter. Around it, and what they would do there is they popped it up on top of the mountain there, okay, that form, and then they would pour concrete in it, and they would let it cure for a bit, and then they would raise that slip form up a ways, and they would get more of the cap, and it cured, they did that for like 4 days straight, night and day, until they got up to that 100-foot mark. Okay, now that's what the telescope is actually sitting on. The exterior portion of the building isn't in contact at all with that pier because when the wind is blowing and everything, and they can operate, I think, up here to like about 45 miles an hour. So when you get above that, they'll shut everything down. But so, you know, if you got like 30, 35 mile an hour winds buffeting the outside of the building, you don't want that being put into the telescope and the mount that it's sitting on. So for that reason, this is actually two sections to this observatory. The intersection. Well, let's see how many we can get in here. Oh yeah, we got some around here. We can do it. Come on. You got room. We got room. Come on.
You sure? Because we wait.
No, that's it.
I'm a bit claustrophobic.
This will only take 30 seconds to get up there.
Okay.
Okay. Ready?
Unless it breaks down.
Excuse me.
Hasn't done that for weeks.
Okay, we're up 100 feet.
Right now?
Yep. Like it says right here, we're going up. Well, that didn't sound good.
That was fast for 100.
I think so. Out the door.
Stand bump room. What is that? Bump room. Yeah, what is it? Bump room.
Can you tell me?
I kept the train on.
side of the building, coming in contact with the telescope and the pier and everything. Well, if you look at the steps here, you can see that they don't go all the way to the floor. They're about an inch or two above the floor. So that shows you that it's isolated. Okay, now the way this thing would work at night is they would raise the shutter on the dome, and this big silver thing here is the shutter. So it would go up like that, kind of like the door on a garage door. So it goes all the way back like that. Then that exposes the telescope to the nighttime sky. Then what will happen is the astronomer or the telescope operator or the astronomer in the observing room, which is up there that you can't see, will decide what object he wants to look at. Okay? So he'll say, okay, let's look at NGC 861, and they will go to their computer screen. They will look at the sky map. They'll find NGC 861 on there. They'll click on it. Then what's going to happen is the telescope will automatically rotate to that portion of the sky where that object is. Then it will lock in on it, and then it will continue throughout the night to track it from east to west. Now, at the same time, the dome will also track right along with the telescope, because remember that the telescope will always has to be pointed out through that slit in the dome there. So they're kind of linked together. And the way they know, the way the telescope knows where the dome is if you look right above here, you can see all those like UPC codes up above there. See them up there? So that gives the telescope an idea of where it is.
That's the
So this telescope is, it's built like a battleship, but it's got to be as accurate as a Swiss watch in essence. Now the two, I forgot to bring my key along, but the two different orientations that are involved with this telescope are what they call right ascension and declination, okay? So the telescope can move in right ascension or declination. Right ascension is having the telescope move from east to west. Declination is moving the telescope north and south. Every object in the sky has an address, okay? It has a right ascension and a declination associated with it. Just like, everybody's house has a street address. Well, every object in the sky has an address too. So when that astronomer in that control room decides to go to that particular object, when he clicks on that object on the map there, it just then knows to go to that particular right ascension and declination address.
What moves here? What moves?
The telescope will move. It can move this way.
The white part?
Right, yep.
That's the only thing that moves?
It moves, and then you see this big horseshoe thing here? That'll move too. Like I say, you can see it over here. The white part moves this way. So that's north and south. And then this whole yoke will turn this way. It's resting on these two pads down here where there's high pressure oil that gets injected in there. And that's how it rotates. It only takes about a quarter horsepower motor to get this whole 700,000 pound thing moving here. And once it gets moving, all you got to do is really push it by hand and it'll move. It's so finely balanced and everything. Now, the way the observers observe, nowadays they do it from a control room, because what happens is that usually their instrumentation is located at the bottom of the telescope, and that cage work there is called the Cassegrain cage, and that's what the instrumentation guys kind of work out of, so they can stand in there and put instrumentation on the bottom of the telescope. I don't know if you can see it. Yeah.
You can see it from here.
Yeah, okay, so all the instrumentation is right at the bottom of the telescope, like the cameras and spectrometers or whatever kind of stuff that they're using for that night. And all that stuff is electronic, digital. And all that stuff gets fed into the control room and up on the monitor screen where they can look at the data. Now what's interesting about here too is nowadays it's getting to the point where the astronomer doesn't even have to be here anymore. What they've been doing here about a quarter of the time now is Skyping with the astronomer, like he could be in Tokyo or something, and he could be looking at the same data and everything that the telescope operator right here is doing, so he doesn't even have to come here anymore. It's kind of neat. Now, when this telescope was first opened up, the idea for this observatory, you know, as big and as high as it was a couple of things. First of all, they wanted to get it high enough off the mountain so that when the winds came over it, those winds would be below it. Because if you get air movement and everything above your telescope, that's not good. You try to have very steady air above your telescope. That all helps the seeing thing, you know. So they built it up high to be above those winds. The other thing they did, the reason why it's built the way it is because they planned on actually having the astronomers living in this building, okay? They're going to do their cooking, cleaning, sleeping, everything. So anyway, that's the way it started out. Christmas came along, and all the astronomers left the building except for one. He decided to stay here, and he was going to continue doing, I'll call it imaging, but back then they were using film. So anyway, he would sit up there at the telescope, even the prime focus way up there at the top, and do his guiding and everything on an object for all night long. And he went down and looked at his images, the stars and everything. They were really nice and pointy, you know, really good, you know, just like an astronomer wants. So he thought, oh great. So he continued his work while all those other astronomers were gone and everything, and great. Then all the astronomers start coming back, okay? They move in here again and they start doing their cooking, cleaning, and all that stuff. And the images that he started getting now were all fuzzy again. Well, these guys are pretty smart. They were able to figure out what had happened. By having all these guys move back in here, what they did was they added a little bit of heat, probably a whole bunch of humidity and moisture. And this place is like a great big chimney, you know, and it would rise right up through the building and then out of the top of the observatory dome, and that was messing up their seeing. So at that point they moved everybody out, got separate dormitories, cafeteria, etc. Then in like 1996 or 95, they cut a lot of these vents that you see just above the windows here now all around here to make sure that you got a good airflow in here, make sure that the temperature of the telescope and the observatory are the same as what the temperature of the outside night is going to be, you know. That's very important that you have the temperature of the telescope mirror and everything at the same temperature that nighttime temperatures are going to be. Because if your telescope mirror ends up being a little warmer or something, well, in the nighttime a little cooler, well, you get some condensation, plus you get air currents coming up off of that telescope. That just messes up your seeing something terrible.
What's this fenced-in area?
Good question. What that is when they take the telescope mirror out, every once in a while this mirror has to be re-illuminized. You know, all the old aluminum take off because it's starting to go to pot, you know. So what they'll do is they drop it out of the telescope, and they take it over here, and then they take it down into the building further where they have this vacuum deposition chamber that I mentioned before that they end up putting a new layer of aluminum on the mirror. So that's what that's for. Okay. Any questions? Now we go down to one
What's this net for?
It's just a safety net. In case somebody falls out of the cage there, or they drop a wrench or something, catches it.
Yeah.
But yeah, like in the olden days, they would actually do their observing out of what they call the prime focus, which is right up there where that black tube is. And the way things would work then is light would come down from the star galaxy, come down, hit the big 4-meter mirror in the bottom of the telescope, bounce back up into what they call the prime focus, and that's where they would have their camera in that would, you know, photograph the image. And because they would have to, because film is so slow and it takes so long to collect an image on film, they would have to sit up there all night, and they would have to very, very closely guide that image. You know, they wouldn't want it to move around a whole lot, otherwise it would blur the telescope, blur the image on. So they would actually have to physically, with a little hand control, you know, move the whole telescope a little bit by a little bit to keep it, you know, exactly on that star or galaxy that they were looking at. So obviously, if you need to stay awake and you drink a lot of coffee, then you're going to go over. So it's a very difficult spot to be in. Nowadays, they don't operate that way anymore. They operate out of mostly out of the Cassegrain focus, which is at the bottom of the telescope, and all the instrumentation is there, and all that data ends up getting collected and observed. There is no eyepiece. Good question. Okay, any other questions on this?
Just checking.
What's
Where
that
did-
ladder up there for?
To climb up.
For what?
Maintenance or something. All right, let's go down to the next level. I'll show you guys a few things down there, and then I'll let you go.
Vraiment, combien de personnes travaillent ici en permanence? Quand je veux dire en permanence, qui disent même travail là,
You shouldn't get under the guy that's sweating there. He might trip on you.
It's good.
Moi, ça s'ouvre. Ça va s'ouvrir. Ben oui. Regarde, oui. Et puis, alors, vous avez vu comme il est là. Ici, on va se
The telescope has to move. It'll do a 360 in about 5 minutes. It moves pretty quick.
And the actual elevation of the base of this building, please, what's the elevation?
Over 7,000 feet. It said on.
What was it?
Yeah, there's a sign in there. 7.
So it's over 7.
Yeah. Once you get up on
Can I see?
Okay, somebody asked about eyepieces and telescopes, professional telescopes. Now, professional astronomers don't use eyepieces. They have all these other fancy sensors and stuff and equipment that they use, such as, what's this here? An infrared camera. So an infrared, the camera is probably a CCD camera. So that's CCD cameras are kind of like, what the Canon is or whatever you got in your phone. Infrared means it's just going to be able to see that portion of the spectrum just beyond our ability to see in red. And so that's what that is. You have an infrared cryogenic spectrometer. Once again, it's infrared, so it's going to see that little bit of the spectrum that our eyes just can't quite catch. Cryogenic means it's cool. A spectrometer, that's a device that splits up constituent light of a star or galaxy into its constituent colors. And by looking at those, and some of the black bands and white bands that are visible in it, you can figure out a lot of things about a star or galaxy, like how far away it is, how fast it might be moving, what direction it's going, how hot things are, all these other things. And the reason why it says cryogenic is because a lot of the cameras and equipment that they use on telescopes ends up being cooled like down to minus 150 degrees or something like that. The reason being is that cameras in that are a lot more sensitive when they're really, really cold. For one thing, a lot of the cameras, if they're doing infrared imaging, cameras can pick up heat real easy. So you don't want anything very warm around it. So you got to try to cool everything off around that camera. The other nice thing about cooling the instrumentation cameras and such is it reduces the electrical noise that those things can produce. Like the CCD cameras, you get what they call these hot pixels in that. Whereas if it's at room temperature, but if you make that camera really, really cold, like I said, maybe 150 below or something, you don't get those little hot pixels anymore. And what creates those is this electrical noise, which is just electrons bouncing around. If something's really hot, that means the electrons that it's made of are moving around really, really fast. That's what it means when it's hot. But if you cool something down so that it's like near absolute zero, well then those electrons and that don't bounce around at all. And because they're not bouncing around, they're not creating noise and making little white dots on your CCD camera that are those stars or is that electrical noise? So that's why the astronomers like to cool down their cameras and spectrometers and all this other stuff. Shell spectrogram, another spectrogram. I was talking about spectrographs and spectrometers and such. This is just a device that, like I said, takes the image of a star or galaxy, and it turns it into its constituent colors, by looking at that and looking at the lines that are produced, you can actually determine a lot about the object that you're looking at. Without that luxury, without that ability, we wouldn't know hardly anything about the stars and galaxies that we know about today. Okay, let's go in here and look at a few pictures.
one? Oh, here. Is this one?
And the Orion Nebula is located in the constellation Orion. It's pretty easy to see with her binoculars, even with your naked eye up here in a dark area. So what's happening here, this is actually a place where stars are being born right now. This is only about 4,200 light years away. So this is the closest place where there's stars being born to us on planet Earth here. So what happens is you've got this great big nebula here, and there's all sorts of hydrogen and helium in this cloud, okay? And what happens is as gravity starts pulling all this hydrogen and helium together until it starts actually forming what they would call a protostar. Well, this protostar will continue to grow, and gravity will continue to pull material into it until it gets to the point where it gets big enough, massive enough, and hot enough that it actually will just, all of a sudden turn on and be an actual star. And once the core of that thing gets to around 27 million degrees, that's where that occurs. 27 million degrees at the core of a star, that's where hydrogen, which is the most basic, most prevalent element there is in the universe, but once you get up to around 27 million degrees there, fusion occurs, and that is the process that really keeps all the stars and our sun going, is this fusion process. And on our particular star, our sun, every second about 700 million tons of hydrogen is fused into helium. So there's about a 5 million ton difference there, okay? Well, anyway, if you remember Einstein's formula, E equals mc squared, energy equals mass, basically, so that the mass is that 5 million tons of material, and the energy is what the sun is producing by heat and light and everything. So that's that formula actually at work at the very core of a star or a sun like ours. Now, so this is how stars get born in big clouds of gas like this. That's probably how ours formed one day 4.5 billion years ago. So they'll live their lives, kind of like our sun is right about middle-aged right now. It's about 4.5 billion years old. It'll keep going along for probably another billion years or so. And it's right at its core. It's right now converting hydrogen to helium. At some point, it's going to be mostly helium in that core. Then what's going to happen is going to start burning the helium. When it starts burning helium, it's going to start converting helium into oxygen and carbon. And once it starts doing that, then our sun is going to start expanding. It's going to start cooling and actually expanding and get more gaseous. It's going to actually turn into a red giant star. When it does that, it's going to expand out to probably Earth's orbit, and we'll be toast. And that'll continue on. It's going to keep blowing off these shells of oxygen and carbon and everything. It's going to produce what they call, if you look here, it's going to produce what they call a planetary nebula, as you see here. So someday, some astronomer, maybe a billion light years away from us, might point his telescope towards us, and where it once used to be our star, he'll see this little gaseous ring here with a little dot in the center of it. Well, that little dot in the center is what used to have been our sun. It's now called what they call a white dwarf, and it'll be about the size of planet Earth. But there isn't going to be any fusion process going on in that little white dot there anymore. It's going to be more like a burnt out ember of a piece of coal or something. But that'll last for a long, long, long time. Like I say, it's about the size of Earth, but it's incredibly dense. Like a tablespoon of it might weigh as much as like 20 African elephants or something like that. It's really dense material. And it'll just kind of keep glowing there for billions and billions of years. So that's how our sun is going to meet its demise. It's not going to blow up or anything really neat like that. It's going to go kind of out with a whimper. But when you get stars that are 6 or 7 times larger and larger than our sun, then they go out a lot more cataclysmically. What happens then is, even those really big hot stars are converting hydrogen to helium at the core. Then it goes from helium to carbon and oxygen. But since they're so big and massive and everything, they go past carbon and oxygen, and they keep working their way through the element. Finally get to a point where it's actually going to start forming iron in the core of that star. And when the minute it starts forming iron at the core of that star or star, that's when it's going to explode. Because all these other processes with hydrogen, helium, carbon, oxygen, energy kind of gets dissipated out. But what happens is when you get iron at the core, and it's called the exothermic process, I think, what happens then is all that energy that was blown out starts getting pulled right into the center of that iron core. And as soon as all that energy gets pulled in, it's like boom, just like that. And that thing will blow up, and it will put out more energy and light than our sun will in its 9 billion year life. And so then all that material that was in that star gets scattered throughout the universe in essence. And that's how all the heavy metals are made, gold, silver, carbon. Well, carbon can be made in a thing like our sun is going to do. But anyway, it's in the explosions of stars and planetary nebula, like I explained with our sun, that all the material that our Earth is made of, it's all the material that we're made of. We're carbon-based, so our carbon comes from stars exploding and everything. All the air in our bloodstream comes from supernova explosions that maybe blew up billions of years ago. All the stuff on our planet is from stars and stuff that blew up billions and billions of years ago. We're literally made out of star stuff, literal. Yeah, it is. I mean, what's the material in your right hand might have come from
How long does it take for? You say it's really quick, but as soon as it turns to iron, is it like instant?
It's pretty much instantaneous.
And where we can't say like, oh, in a day it's gonna reach us or something.
No, it happens just like that. From what I understand, it's pretty instantaneous. It doesn't take very long.
Okay.
It's kind of like, an astronomer might be looking at this galaxy some night, M81. And this star here, you won't see it, okay? All right, now the next night the astronomer looks at this galaxy and boom, there's that star. That's because that thing just blew up. Yeah. Oh, the other thing too is once one of these stars blows up, one of these things blow up, it isn't necessarily a complete end of that star. Two things can be created after a supernova explosion. You can either end up with a black hole that's left, okay, or else you can end up with a neutron star. Now, of course, a black hole is incredibly dense. It's so dense that light can't even escape from it or anything like that. But then a neutron star is also very dense. And it's so dense that if you took that tablespoon of neutron star and dropped out the window there, it would go right through the Earth. It's that dense. And what can also happen with a neutron star is sometimes those things will start spinning, okay? They'll spin. And they spin rapidly enough. They can spin like the one in the Crab Nebula, which is an object you can see with a modest-sized telescope. Crab Nebula, there's a pulsar in there. That thing spins around 30 times a second. This thing is probably about as big as New York City in diameter. It goes around 30 times a second. And what happens is that you have these jets that are coming up off of that neutron star that come out of either end of it. And if one of those jets is pointing at us, that's when we get that little pulse of energy. And then when it gets like this and it's not pointed at us, it's not there. Then when it gets over here and that other pulse is pointed at us again, we get, oh, there it is again. So those things can spin around even faster than 30 times a second. And we're actually able to they first picked that up in the Crab Nebula with a radio telescope. And then back in 1968, actually using the Stewart telescope that was brought up here from the campus in 1963, they actually used that telescope to actually optically see the first neutron star.
Can you actually go through time with the wormhole thing?
That's not my favorite. I don't know.
Or like a black hole, like like at the other end, like you know, they say it's like a spiral. You know.
Like why they call it black hole? They don't know what it is.
There's a lot smarter people than me that know that too. I got something in common with geniuses.
What's over there?
What's that? What's over there?
Straight road.
Oh, okay, that road there, at the end of that road is the ranch where the contract was signed for Kitt being purchased by, I don't know what.
Where's Tucson?
Oh, Tucson would be right over there. Now, if you look around here, you're gonna see some photographs with some names and stuff on it. Will tell you what everything is as you walk around up here. They can probably tell you better what everything is. So anyway, that's all I have unless you got some more questions. Good? Okay, just take a walk around here and look at the sites. It's pretty neat. So, okay? Very good.
Thank you.
You bet. Thanks for coming. Thanks for coming.
Thank you.
Thank you.
Thank you.
You bet.
So in every single this is stars right there.
Those might all be galaxies.
Galaxy.
Yes.
So they're all each have their own energy.
Yeah.
That's why they're bright. Like
Well,
this.
every galaxy, like this for sure is a galaxy. And that galaxy there is kind of like our galaxy probably, meaning that this galaxy here probably has 1 to 200 billion stars in it. This galaxy here probably has 100 to 200 billion stars in it. Maybe this one too, this one. So, I mean, there's probably 100 to 200 billion galaxies out there, and each galaxy has maybe 100 to 200 billion stars.
They have their own energy. That's what we can
Yes,
see.
yep,
That's what
they're all stars.
That's the stars that we see out there, right?
Well, these are galaxies. These are just kind of like our Milky Way. Our Milky Way is our galaxy. Well, this is there's probably maybe there's a star in this galaxy that has a planet on it with people on it. Well, that would be their galaxy. And there's literally billions of galaxies.
And the stars that we see out there,
The stars that we see in the night sky are all stars that are in our galaxy.
there are stars like planets reflecting the sun.
It's amazing.
Planets reflect the sun.
Reflecting the sun, right?
Yeah,
That's what we can see.
Stars create energy. The planets just reflect the energy from the sun. Yeah. Even the moonlight is reflected sunlight. And everything when you see a planet up there, it's just reflected light from the sun.
All the stars that are like planets.
Well, all the stars are their own energy-making machines.
So the ones that we saw.
Yep, they all make, just like our sun creates energy using that process I was talking about, the fusion process. Well, every other star in our galaxy does the same thing, and every star in all these galaxies does the same thing too. These are all separate galaxies for sure. Now these might be stars, right? If there are stars, they're stars that are in our galaxy.
So we don't see any galaxies with our naked eye? Is that?
Yes, the Andromeda galaxy.
Just
That's
the one
only
you were
that
talking about,
can-
yeah.
Yes, that's like 2.5 million light years away.
Right.
So
Just one.
when you go out, if you can go out and look at that thing, if you knew where exactly where it was, you could, and you're in a dark spot, you can see with your naked eye. So that's 2.5 million light years. So that means that the light from that galaxy left 2.5 million light years, or 2.5 million years ago, and didn't come into your eye until tonight.
Yeah.
So it's been traveling 2.5 million years to get to your eyes.
Yeah. That's kind of cool.
Yes, it's
incredible.
They say astronomy is like a time machine because when you look at these stars and galaxies that are so far, far away, that not only are they far away in distance, they're far away in time too.
So I mean, so I'm saying, so each one of those stars, the ones we see up in the night
Sky?
I mean, they're all stars, and they're creating their own light.
Yes.
That is coming to us from 100 light stars, 100 light years.
It could be, yeah. The closest one is 4 light years away, but there's others that are 100
So
light years away.
for all we know, like the planet you think you're looking at right now, that's like 200 million light years or whatever. If you're looking at a planet, it could have like people on it, or it's a different type. Because you're 2.5 million years behind, like something could have happened to it.
Oh yeah,
like,
I mean,
like what happened to Earth.
like,
you
well,
know?
what happened, like with M31, that galaxy I was just telling you. I mean, something could have blown up completely and be completely gone, and we wouldn't know about it yet because it takes 2.5 million years for that light to get here.
So there's probably like another field over here in this galaxy.
I hope.
Going like, see right here? That's the Milky Way right there. There's probably people over there.
Yeah, that poor guy.
probably talking about telling
And he's
people.
probably full of it too.
All right, well, thank you very much.
Okay, you
Thank
bet.
you.
Okay, you have a good day. Podría estar mirando una planeta. Ellos están mirando para atrás, pero ellos están mirando a los dinosaurios. They could be looking at the dinosaurs. This planet is so cool. That's some undomesticated creatures that are dinosaurs. In reality, 65 million years ahead, or standing here, we're actually here at this. Except that the light that the dinosaurs reflected off the sun, those tiempo estaban. Yeah.
Pero ¿cómo harías? Uno solo mata, están viendo los dinosaurios, como alguien más en otro planeta.
Ajá, si alguien ahorita podría estar parado en la neta aquí.
Did you find the planet Aho in there?
Ellos están mirando
Yeah.
para acá y están mirando.
The Aho mountain here.
Qué suave, mira, el otro planeta.
Point that out again.
Huh?
So point that out again.
Son como criaturas que no tenían brazos. Y yo veía pero de verdad, eso era 65 million years. And we're actually standing here. There's the light takes time to travel. Luz no es directo. El lazo de luz dura 10 minutos a llegar a
Trying to sell some pinchy bugs around the world.
dura el tiempo en ir para el espacio. No, porque duró 65 millones de años
Oh, we're right here.
para llegar a su planeta.
Oh, really? You can see us.
Él está mirando. Si estuviera alguien en 30 millones de light years, miraría como personas primitivas. No, primitivas, va a ser como 25 mil años. Miraría como personas así como están
Huh? Yeah, and I brought a spare dead battery too. Just the other one was not dead yet. It was just getting low, so I figured I'd change it early.
That would be scary to get on there.
You think so?
Yes. Especially if you're afraid of heights.
Darn it.
In yourself right here. We could go to that store and get some Gatorade there.
Uh huh.
I get some soda. They always have the sale on soda at Baptist store.
Batches. All right. Is this battery any better? No. Got another dead battery. I don't know. Did you want to walk in a circle and go back?
I think they went up the wrong way.
Yeah, I brought two dead batteries. The one I had was
You need to just get up.
was in a hurry.
Charged up.
Well, there's plenty charged up. I just didn't bring the right ones.
You gotta go up this way. Or do we go up that way?
Where?
This way out, right here. This is right here.
Let's go up here. Let's see.
Right here. This way out.
This way. This way now. What you going up there for? It's this way. Is this the button? Want to go down the fire door stairway?
Be tiring. We're locked down.
Pump room. Authorized personnel only. What do they pump in there? Do you want to go down or up?
Yeah.
You. 3, 2, 1. No smoking. Do you think they used to smoke in this building? Probably. Maybe not in here. I don't know.
He's off walking down the road.
We're speaking French.
Is that what you're speaking?
I think so. Let me take a picture here. Way up where? Uh-huh. Why does it say I got 33?
It's a guide. He just left us.
You're on your own. I'm on my lunch break. Did he walk fast there? Or did he take a car or something? Like he had a car up here? Drove down? He probably drove everybody else down. Did you want to jump down?
No.
You can slide down on a piece of cardboard? Boom, boom, boom.
You don't know those rocks are solid.
Get some
Step on
cactus.
one and it'll probably roll. You could come up anytime you pay. I don't.
Pay for what?
To go into, you know, what, I guess, do they charge?
They didn't charge anything for this tour.
I know. Maybe this would be kind of, you want to go to the other places.
First on the night.
Charges and what they were. It's nice and cool up here. Take your jacket up.
No, it's okay. I'm fine. I like this way I can sweat more. You just want me to take my jacket off so you can wear it.
No. Talking about the scientists and
That's scary to you there? They spend all that time looking through telescopes into people's windows. The just pointed over at her house. She's the infrared, huh? I saw some big lake on the reservation. I don't know what it was. Did it start with a M or something? What was it called? Have you seen that big lake they've got? It's like a huge one.
Where? Out here?
It's on the reservation somewhere.
Oh, managers?
Start with a M, would you say? Yeah. Have you been there?
That's where my mom was born. That's where Floyd lives at. That's why I told him that one of these days we'll drive over and he'd take us to the dam. I remember going there when I was a kid. We used to stay at my aunt's house. And we always walked over there and played around there.
Do you like going downhill better than up?
Yep.
Actually, my knees, I think I have a harder time going downhill than uphill. It's funny when I look at it through here, it stops the fan.
Oh, really?
Because it's high shutter speed.
Oh.
But just the image stops it too on the view screen that I'm looking through. Because it's an electronic one. Get in the stuff with a slip and fall down on my butt. This earlier it said it had hardly any battery. Now it says it got 31%. Are you gonna do that?
Do what?
That pose for me there?
No.
Pues ella piensa que se ve como que está ahí.
Huh? You want me to drive up and drive down?
Drive up and drive down.
Huh?
Walk up and drive down.
No, I'll drive up and drive. After you drive down, bring me the car. Okay. I'm gonna fry the onions with the onions too. Huh? Okay, I'll walk up and drive down. You think these things through would make it harder for me? So, wouldn't it have been easier if I drove up and drove down?
You think that's a gay couple?
Were their legs shaved? Looks like they might be. Looks like their legs might be shaved. Huh?
I don't think it's a father and son.
Maybe they're just hikers. Why are you in the sun? They have matching hats.
There's a light piece.
Hmm.
With different colors.
Maybe they're a border patrol couple.
Do what?
I said maybe they're a border patrol couple.
Could be too. Never know.
And military, they seem a little old for the military. I want to stop up here and take a break, get some air. A microwave tower, and a radioactive view. Oh, my battery's low again. I know. I'm stopping right here. I was trying to give you a break.
That lady was telling asking me if I had a cold or something.
Uh-huh.
For this to start up. I said no. She goes, huh? Because that's how they usually start up.
What's that?
If you have a cold.
Oh, yeah. Your nose is running now.
Yeah.
Is it the
I think
plants and stuff?
could be.
A snake bed? A what? What was the thing was closed here? We'll go use the restroom.
Yeah. They're picking up really fast. A good couple.
There's your tourist guy. He's a Green Bay Packers fan.
He's taking off too.
Oh, there's an outside bathroom here too.
That's good.
Or you go to the one on the inside.
$3.20.
So they close at 4.
Mm-hmm.
Handicap restroom and visitor center.